Okay, so what is mass? This has both a simple answer and a complicated answer. So first, we're going to start with, in a way, a preview of the complicated answer, which is that we have to say what we're using when we talk about mass. Like, what do we mean by mass? And here, we're actually talking about inertial mass. So in general, in this class, when I say mass, I actually do mean inertial mass. And that's fine. I typically take a lot of shortcuts in my speech, and maybe you do too, but I at least right now want to make a slight differentiation between them. So inertial mass is a measure of the tendency of an object to resist a change in motion. So the measure part is in particular what makes it mass. So inertia is the idea that an object in motion resists a change in motion. So we can talk about inertia as that property or that idea. And mass is basically saying, well, let's give it a number. So we'll talk in a little bit about what this actually means. But one thing that I want to talk a little bit about right now is this interesting notion that inertial mass does not equal gravitational mass. So again, if I just say mass, which we're normally going to do, and say, oh, this object has a mass of 1 kilogram. Well, what type are you talking about? Are you talking about gravitational mass or inertial mass? Because there's two types, and they are not technically the same. Now, the caveat is that they seemingly, usually, always are the same. Let me explain. So, inertial mass is this idea that an object resists a change in motion. So imagine holding a styrofoam ball in one hand and a steel ball in the other. And now you want to shake them back and forth in the horizontal direction. Now it's going to be much harder, much more difficult to shake the steel ball back and forth than it is the styrofoam ball. It has a bigger mass, so moving it, changing its motion, is more difficult to do. We don't normally think about that when we think about mass, but that's actually what inertial mass is. And there are ways you can specifically measure it by basically putting it on a device that tries to shake it back and forth. Now, gravitational mass is actually what we normally think about. Gravitational mass is how strongly is this attracted to another large object, i.e., for us, usually the Earth. So gravitational mass is what you get if you put your object on a scale, right? So I have a scale with something, and maybe it gives me my value in newtons, maybe it gives me my value in pounds or grams, whatever. But this is the idea that we're talking about the force of gravity and how strong is that for gravitational mass. Inertial mass, again, is saying, well, what happens when you try to shake it back and forth? So these are two different things. These are two different concepts in physics, and they show up in different equations. However, for reasons that physics doesn't have the ability to explain yet, they are always the same. If I give you a block of steel that has a gravitational mass of 1 kilogram, it also has an inertial mass of 1 kilogram. Again, this is where people are like, oh, well, maybe we can get this sort of thing from, say, general relativity. But from a classical physics point of view, from a Physics 202 point of view, these are two different ideas, and there's no reason why they have to be the same. But they are, and again, we would need something like general relativity to explain why these two things are the same. That being pulled towards the Earth and being shaken back and forth are actually different things. So we will never talk about this again. Again, I think it's a cool thing to know about because it's one of those weird things in physics that normally we don't think about, but it's a little mind expanding in a way. And we can just call it mass because these always, that's not how you spell always, that's how you spell always. These always happen to be equal numerically, right? The number works out to be the same. We can actually simplify it down to mass. But conceptually, they're different things. If you didn't follow that at all, that's fine. Like I said, I think it's really cool. We'll never talk about it again. Okay, so if we want to say why do we care about mass, why are we talking about it right now, mass is effectively the proportionality constant between force and acceleration. Now I am going to write this equation this way. You might know it written this way, which is fine. And I want to point out that right now we're talking about one force and it's constant, okay? So here, what's on the x-axis is the mass, the number of kilograms, and what's on the y-axis is my acceleration, and so this is for one constant value of force. So note that this doesn't look proportional because this would be a 1/m relationship. But the point being that for 1 kilogram with a certain force, you get an acceleration. If you double the mass, which is on the bottom, you've divided your acceleration by 2. If you have a mass that is 4 times as much, you've divided your acceleration by 4. So this is what we mean when we say that inertial mass is the resistance to change motion. And remember that acceleration is a change in velocity. So to apply the same force, if I have a bigger mass, it changes its motion less. The acceleration is less. So the reason that we write the equation this way is that it is more clearly showing you cause and effect. That F, force, is basically the cause. You're applying a force. Mass is a parameter, and acceleration is going to be the result, the effect. So that's part of why we write it here, to hopefully make that more clear. Now we are about to make this equation a little more complicated. Right now we're mostly still working with that experiment we started with, so we're talking about only one force, and we're going in one direction. So that's why this still is simple. So this isn't yet our general equation. I wouldn't call this yet Newton's second law. Briefly, now that we've met all of the pieces that we need of forces and that we're dealing with them quantitatively, we want to define the units. We call the units of force newtons, i.e. after the guy who figured out a lot of stuff about forces, and the symbol we use for it is capital N. 1 Newton is defined as 1 kilogram times 1 meter per second squared. And one way to see this is if we use the other form of the equation where it's written that way, our units on this side are kilograms times meters per second squared. That's an S. So that's what we have on the right. So what we need to have on the left is the same thing, which we would call a Newton. So kilogram meter per second squared, and again you could see this written different ways, kilogram meter per second squared, or kilogram meter second squared. It's all the same thing. And so we can define 1 Newton to be the force needed to cause, right? The force is the cause. A 1 kilogram mass to accelerate at 1 meter per second squared. Again, this is the situation where we're only worried about one force. We're about to get to Newton's second law and make this a little more complicated.